Hello everyone, my name is Jonathan Smith Cabello Rojas. Today I'm going to talk about how quantum physics actually explains Newton's laws of motion. For centuries, Isaac Newton's law, the laws that describe how objects move, were seen as the foundation of physics. They work perfectly for everyday things like cars, footballs, and planets. But now we know that the universe is built on something deeper, the strange and fascinating laws of quantum mechanics. In the quantum world, particles such as electrons or photons don't follow just one path. According to the physicist Richard Feynman, every particle explores all possible paths between 2 points. That means if a photon travels from light source to your eye, it doesn't choose any other route. It tries every possible route. Each path has its own phase, like a tiny rotating arrow. And when we add all those arrows together, most of them cancels out. Only the paths that take at the almost same time, the ones close to the shortest or the fastest route, add up strongly. That's why light appears to travel along the path of least time, exactly as Feynman's principle predicted hundreds of years ago. In other words, light doesn't know which way to go. It just tries everything and nature itself filters out the rest. Feynman extended this same idea to matter particles, like electrons. He proposed that all particles have kind of quantum clock that ticks as they move, and this ticking determines their probability to be found in one place or another. This leads to the famous de Broglie wavelength, which says that every particle has a wavelength depending on its mass and speed. For every small particles, the wavelength is large enough to create interference. That's what gives us quantum effects. But for big objects like a football, the wavelength is unimaginably tiny, so tiny that the quantum behavior disappears. That's why in our daily lives, everything seems to move in smooth, predictable ways. Quantum behavior fades into classical motion. Feynman also showed that the rule explores all paths naturally turn into another powerful principle, the principle of least action. This principle says that nature always follows the path where a centered quantity, called the action, is smallest. The action depends on both kinetic energy and potential energy, and minimizing it, giving the correct motion for any object. When we apply mathematics to this principle, we get Newton's second law. Force equals the rate of change of momentum. So instead of starting with Newton's law, we can start with quantum physics and derive Newton's law as a special case. That's one of This shows us that Newton's world and the quantum world are not separate. They are two sides of the same reality. At the small scales, the particles behave like waves, exploring all possibilities. At larger scales, those possibilities merge into one clear path, the one we see every day. In short, Newton's laws are not wrong. They are just an approximation of a deeper truth. Quantum physics doesn't replace classical physics, it explains it. At the deepest level, nature explored every possible path, every route, every option. But when the numbers add up, the result is simple. We see only the path of least action, the path predicted by Newton's law. Thank you.